Thank you very much. First of all, to the organizers for inviting me here and for setting up this nice conference. And it's my second time in Seoul, and I've had a very nice time last time, and I hope I'll have a nice time this time too. This talk, I should say, first of all, is based on work with Kyriakos Papadimos and on these three papers. But we've also been, made a lot of progress after these three papers, which will hopefully be published soon. Some of that is additional work with Kyriakos, but also with a postdoc at ICTS, Prashant Samantre, and Shouvik Banerjee, who's a postdoc with Kyriakos at Groningen. So these are my collaborators, and all this work that I'll talk about is work that's done with them. So let me start by giving you a summary and overview of my talk. As many of you know, but I'll just remind you, there's a very robust prediction from effective field theory, which is that if you look at quantum gravity effects and you look at quantum gravity effects about a black hole, then these quantum gravity effects could be very important near a singularity, but are generically not very important about a big black hole. And in particular, as you take the radius of the black hole to be much larger than the Planck length, these quantum gravity effects become more and more unimportant. And this is a very robust prediction from effective field theory. What has happened is that in the past few years, and actually this started with the work of Samir Mathur, although it was popularized and expanded upon greatly by the work of Marolf and Pulczynski, Almeri, Sully, and Stanford. Many people have pointed out that in fact it appears that the information paradox is so severe that in order to be able to resolve the information paradox, you have to give up this very robust effective field theory intuition that quantum gravity effects are important only near a singularity. And in fact, it may be the case that quantum gravity effects are actually important all the way out to the horizon. Okay? So this is what this entire firewall debate has been about. And our work in this has basically been to try and rephrase this debate as a debate about local operators in the AdS CFT correspondence, which makes it a much better defined argument. And I'm going to try and describe for you, how we can construct these local operators both outside and inside. The key thing is inside the black hole horizon, and then you can compute correlation functions across the horizon, and they show that these correlators are smooth. And this addresses also all of these arguments that have been made in favor of structure at the horizon. However, our proposal at least raises some interesting issues about local operators and this feature called state dependence, which I'll mention and try and describe, and then I'll try and describe some recent work about this towards the end of my talk. Okay, so this is an overview. As I said, it's organized the way I said. I'll start with a very quick review. Maybe I should stand on this side. I'll start with a quick review, and I'll just give you the setting. Then I'll describe this construction of local operators. I'll describe our construction of the black hole interior. I'll tell you how it overcomes all of these arguments that have been made starting from the information paradox to argue for structure at the horizon. And I'll talk about this feature of state dependence. And in the end, if I hope I'll have time, I'll talk about some work in progress towards a state independent construction, and I'll try and explain what these two terms mean as towards the end of my talk. Okay, so here's a very rough summary of the information paradox, but just to remind all of you, if you think of a collapse of some lump of matter into a Schwarzschild black hole, which then evaporates via Hawking radiation, there are very general theorems in general relativity that tell you that it looks like this radiation has information only about the temperature of the black hole, and if you give it some charges, it might have some information about those charges, but it doesn't have too much information about the initial stuff that constituted the black hole. And so the question, in one way to phrase the information paradox, is, the initial stuff that constituted the black hole had a lot of information, and where is this information gone? And this is sometimes shown by means of this cartoon. You start with a small black hole. You don't even have to take something that's collapsing. You throw in a library into the black hole. The black hole becomes big after it's eaten up the library. It evaporates by Hawking evaporation. But now you have back a small black hole and you have some radiation. And the question is, how is all this information that existed in the library now encoded in this radiation? Okay? So that's one way to phrase the information paradox. Now there's a very quick answer to the information paradox, which is the answer that most string theorists would have given you a few years ago, which is that, well, this argument that the radiation knows only about the temperature is after all only approximate. And there are actually strong or there are small correlations between different things in the radiation. If one photon is going in this direction, you look at some other photon that's going in that direction, there's some very small and tiny correlation between these photons, and this information of the library is actually encoded in these photons. Okay? So that's the answer that people would have given you. But starting with the work of Mathur, and as I said, AMPSS, the information paradox started to be sharpened, and I'll describe for you one of the central arguments that they made. And they started to say, look, this argument that you're making about small corrections is too quick, and in fact it looks like small corrections can't carry the information so easily. Okay, so I'll try and describe the arguments, but I'll also try and point out the loopholes in the argument and point out how our construction can indeed give you something where effective field theory holds, where you have a smooth horizon, but yet the information does come out in the outgoing radiation. So I'm going to try and point out these arguments because I think even though they're wrong, or at least I think they're wrong, I think they teach us a lot about black hole physics. Okay, so I'll start by giving you the first argument, which was the strong subadditivity argument, and perhaps some of you are familiar with this. But the basic point is to think of three subsystems, and this will appear over and over again in these discussions. And so you take this black hole, which, as I said, was formed from collapse, and in this black hole you allow it to evaporate for a long time. Now you think of the radiation that was emitted a long time back. Okay, so there's been some radiation that's been emitted over the lifetime of the black hole. Then there's some radiation that's just being emitted. So there are two Hawking quanta that are just being emitted, one of which is going outside the black hole, that's this one, and one of which is falling into the black hole, that's the other one that I'll call C. Now I'm sorry this notation is a little unimaginative, but this is how it is. So just please try and keep track of A, which is the old radiation, B, which is the Hawking quanta falling out, and C, which is the Hawking quanta falling in. Okay. Now, as I said, in this talk at least, I'll try and restrict myself to black holes that are formed by the collapse of pure states because it simplifies some of the discussions. We could consider more general black holes where the black hole is entangled with something else, but it simplifies a lot of the discussions of the information paradox to just consider pure black holes where the entire black hole matter starts in a pure state, collapses, and of course by quantum mechanics it should end up in a pure state. Okay? Now consider the entropy of this radiation. Remember the radiation was the system A. There are very general arguments due to Don Page actually, which tell us that if you look at this entropy, so initially it starts at 0. The reason it starts at 0 is that initially the radiation is an empty system. There's no radiation from the black hole at all. Okay, so clearly the entropy, the von Neumann entropy, by the way, the density matrix of the radiation outside is not pure, even though the whole system is pure. The radiation is entangled with the rest of the black hole. So you can compute an entropy. It starts off at 0 because initially there's nothing, and then it starts going up. The reason it starts going up is because this radiation is to a good approximation thermal. Okay? And if you start putting together more and more thermal qubits together, the radiation just goes up as log 2 into the number of qubits. Okay? And of course the factor here is not quite log 2 because there's some temperature involved, but you can see why this starts going up because this entropy is just the entropy of these different thermal photons that are being emitted. However, it turns out that there's a time after which the entropy starts to go down. And you can argue that starting with almost any generic pure state, if you start dividing it into two systems, the entanglement entropy of one part of the system with the other part has this kind of behavior. Okay? And so this curve is something that holds for almost all states in the Hilbert space. And it holds to an excellent approximation. And in fact, it's also true that it goes up almost linearly and comes down almost at a constant velocity with some very small turnover. Okay? So this is a general argument due to Page. But now, think of an old black hole which is beyond its Page time. The Page time was the time where, that curve turned over from going up to going down. Now, in such a situation, that this radiation B, this Hawking quanta B, is actually purifying A. It's decreasing the entropy of A. So if you think of the system A and B together, that in fact is just the system A as it will be at a slightly later time. Right? Because A consists of all the radiation that's being emitted up to some time. So if you think of A and B together, that's the system A as it will be at some time. And we already know that entropy is smaller than the entropy of A as it exists now. Okay? So in terms of these three systems, the radiation outside, the Hawking quanta just being emitted, and the Hawking quanta falling in, you see that you have a relation which is that SAB is strictly smaller than SA. Okay? However, you also know that the Hawking quanta falling outside is is entangled, is almost maximally entangled with the Hawking quanta falling outside. Okay? So these two systems B and C are entangled together, and they're maximally entangled together. And so usually the way you describe this is if you had a simple qubit model, you might say that the system B and C are entangled together in some 0, 0 plus 1, 1 state. So if the photon that falls outside has spin 0, then the photon that falls inside if the photon that falls outside has negative helicity, and the photon that's going inside has positive helicity, and vice versa. Okay? And that tells you that B and C together are in some pure state, and SBC is 0. Okay? And you can make this more precise, as I will try and make a little later in terms of local operators. But you also know that B and C viewed independently are thermal. Okay, if you look at just the Hawking photon that's coming outside, that Hawking photon is something that's thermal. And that tells you that if you look at just the von Neumann entropy of B or just the von Neumann entropy of C, that is strictly positive. Okay? But these three things, which come from some rather very general and seemingly very robust assumptions, look like they're in contradiction with a very general theorem which is called the strong subadditivity of entropy, which tells us that if you take any three subsystems, any three systems A, B, and C, then you must have that SA plus SC is smaller and equal to actually SAB plus SBC. Okay? And here you see you're getting a big violation of that, because we already argued that SAB, which is the radiation plus the Hawking quanta together, has lower entropy than SA, okay, whereas SBC is 0 and SC is greater than 0. So you can see that the four equations on this slide look like they're mutually contradictory. Okay? And this was the first argument. It was actually made by Mathur, but then again by AMPS. And the AMPS, or the Mathur AMPS proposal, is in fact that you should drop the idea that B, which is the particle emitted outside, and C, which is the particle inside, are maximally entangled. Okay? So you should drop the idea that SBC is equal to 0. So is there some disturbance? It's okay. Okay. So you should drop the idea that SBC is equal to 0, and you should use that to restore the strong subadditivity, which is after all something that's a very general theorem in quantum mechanics. But the moment you drop the idea that the particles inside, the inside of the black hole is entangled with the outside in some very specific way, then it's very hard to avoid the infalling observer from just getting burnt up at the horizon. Okay? And in fact, this is what leads to a firewall, which is just behind the horizon. Okay? Now, there are many ways to understand this, but one should realize that this feature of two regions being entangled with each other is very general. The reason our space-time looks smooth is because this part of our space-time is in fact entangled with this part of our space-time. Okay? If I break the entanglement between some region here, okay, that will in fact lead to a firewall even in our space. So this idea that the entanglement between the inside and the outside of the black hole has to be broken to preserve some general theorem is what leads to these very strong, this very strong and dramatic effect of a firewall. Okay, so this is the firewall proposal, and this is the statement that look, you can't get rid of this by means of some small corrections, and the reason you can't is it looks like you're violating the strong subadditivity of entropy at order 1. Okay? And so no small corrections will help you resolve this, and that's why you have to give up simply the fact that a black hole has a smooth interior. Now this, as you can see, is a very dramatic statement, so I'm going to spend the rest of my talk trying to describe some of the loopholes in this argument. Okay. The first thing to do actually is to try and phrase this in a slightly better and more precise setting where you have control over what these different systems A, B, and C are. And that slightly better setting, the one place where we understand quantum gravity, or we believe we understand quantum gravity well, is the AdS CFT correspondence. And the way to phrase, so the first thing I'll try and describe is how you can phrase this entire paradox in terms of local operators. By the way, I should mention that after the strong subadditivity argument, which was the first one argument that was proposed for the existence of firewalls, there have been several other additional arguments that have been proposed, which make the same case, and I'll review those arguments later in the talk. So this is the first argument. It's a good one to keep in mind. It's in some sense where the whole story started, but I'm going to review some additional arguments as I go on in the talk. Okay. So the first, if you wanted to probe whether a black hole has a firewall or not, you might try and ask, what is the question you should ask in the CFT to see whether there's a firewall at the horizon of a black hole or not. And the first question you need to answer in that is the issue of how you probe local bulk physics from the conformal field theory. Okay, so that's the first question that you have to ask in this game. So even before you try and go behind the horizon, you could ask, how do you probe local bulk physics if you're an empty ADS? So how do you probe local bulk physics from the CFT, if you're outside the horizon of the black hole? That's a simpler warm-up question. And in fact, many people have worked on this question, which includes starting with the work of Benner, but also by the work of Kabart, Lifshitz, Lowe, and in fact some more recent work also by Rosenhaus and Sujong Gray also, who's here. So if you look at local operators outside the black hole, it turns out that there's a reasonable dictionary you can write down that tells you that, given a CFT operator, you can smear the CFT operator in some non-local way on the boundary to generate another CFT operator which behaves the same way as a local field in the bulk. And there's a pretty precise formula you can write down, which is that, you take a CFT operator, you take some generalized free field, which could be the stress tensor or, say trace of f squared, or some other CFT operator which you believe corresponds to a local field in the bulk by the usual AdS CFT dictionary. You take that operator, you Fourier transform it, you look at its modes in the sphere, you Fourier transform it in time, you multiply it by some functions which I haven't written down but we could write down, I can tell you what these functions are, and then you sum over all of these modes. Okay? And this gives you some other CFT operator. It's just a non-local transform from the CFT to another CFT operator. However, this operator now behaves exactly the way a field in the bulk does. For example, it obeys the AdS equations of motion to leading order in 1 by n. And if you correct this map, you can make it obey the perturbative AdS equations of motion with some interaction in the bulk. Okay? So you declare that this CFT operator, which has some, now notice this CFT operator has an additional coordinate. It has this radial coordinate as well, is in fact probing local physics for you. This is this bulk to boundary dictionary phrased in terms of local operators. Okay? And so now the question you want to ask is, if you take this operator and try and put it inside a black hole microstate and try and ask compute a correlation function across the horizon, is that correlation function smooth or does it have some singularity at the horizon? Okay. So that's a way you would use to probe local physics in the bulk and ask the question of the firewall. However, before I ask that question, I have to tell you how to extend this map, how in principle I need to extend this map behind the horizon of a black hole. So to do that, before I do that, let me just try and describe for you some semi-classical intuition and what is it that we expect behind the horizon of the black hole. So let's imagine some CFT where you created a black hole by injecting some matter from the boundary. So you have some matter which goes in and collapses into some singularity. We are not actually at this point so interested in what happens if you probe the region close to the infalling matter. Okay? If you probe the region there, it's possible that all sorts of crazy things are happening which depend on the details of the matter. But what you're interested in is in this red box P, which is a time after the initial perturbations have died down and which is yet far from the singularity. Okay? So the infalling matter is here, is far away from this box P. This box P is also far away from the singularity. And this is the place where you expect something universal to happen. Okay? And in fact, the No-Hair theorem in general relativity tells you that if you look at this point P, then it's only the mass, charge, and angular momentum of the black hole. That's important. Okay? Let me just try and say that in another way. If you think of a collapsing geometry in anti-de Sitter space, where again, as I said, the matter was injected from the boundary, for late times, for this trajectory of the infalling observer, this black line, the statement is that you can in fact replace this geometry with the geometry of an eternal black hole, which is a black hole which has existed for all times, which doesn't know about this infalling matter. Okay? And that's a statement that you can prove very easily and very well, within effective field theory. Okay? So if effective field theory holds, then this statement is correct, that for a late observer, for all local measurements that such a late observer makes, it looks to this observer that he is basically living inside an eternal black hole. Okay? What's the intuitive justification for that? So there's, of course, there are these very fancy proofs of the No-Hair theorem, but there's a very simple intuitive justification to understand this, and that's that if you think of two observers, an early observer and a late observer who are both falling into the black hole, it's very hard for the early observer to send signals to the late observer, because you see most of these signals just fall into the singularity. So if you look at this Kruskal diagram, you see that for the early observer to send a signal to a late observer, the signal has to be more and more tightly collimated, and eventually as you push the late observer later and later in time, it becomes harder and harder for the early observer to send a signal to the late observer. And in some sense, the No-Hair theorem is just an extrapolation of this fact, that what happens early on inside the black hole becomes invisible as you go later on. Okay. Now we do have some understanding of what eternal black holes are in AdS CFT, and Maldacena proposed that the dual of yes.
So two boundaries of the space-time?
No. I'm not assuming two boundaries. What I'm saying is that I have one boundary of the space-time. However, if you probe this geometry, which has only one boundary at late times, then local physics should appear to be the same as in the eternal black hole. Okay? So if you look at correlators of some local fields in a single collapsing geometry, those correlators tend to the correlators of an eternal black hole at late times.
So how one can understand the appearance of the other boundary?
Good, that's the question I'll try and ask. Yes, so that's the central question. Good. So in fact, the other boundary doesn't appear, but something else appears. So that's precisely the central question. Good. So Maldacena proposed the dual of the eternal black hole, which is that he said, there are two CFTs which have two boundaries, and these two CFTs are placed in a particular kind of entangled state, and it's this entangled state that's the dual of an eternal black hole. Okay. However, this eternal black hole, okay, you can construct operators in this region too, but if you think of, how these operators come and you think of a Cauchy slice in this eternal black hole, there's one part that's connected to this boundary, and there's another part that's connected to this other boundary, that's the sigma 3 part, okay? So in fact, if you want to construct local operators in this region too, in this forward region, you have to take the left movers from this region and extend them here, and the right movers from this region and extend them into this region too. And in the eternal black hole, you can construct these operators, and they do in fact involve modes from both the boundaries. Okay? In fact, you can write down a more precise formula for the eternal black hole, which is you say that this CFT consists of these modes that come from the left, and this G is a continuation of that F function I showed you some time back, which was valid outside the black hole, plus some other modes that come from the left boundary, but right moving modes, that you extend now analytically continue into the forward region. And there's once again a reasonably precise formula you can write down. Okay? And now the claim is that, if what I said earlier from semi-classical physics was right, that in fact a pure state approximates an eternal black hole at late times, then there's a question, as you asked, which is what is the interpretation of these O tilde operators in a pure state? There's no second boundary here. Okay? So if you have only one CFT, where do these modes that appear to come from the second boundary, where do they come from in a single CFT? Okay? So that's the question that one has to ask. And you can actually phrase this more precisely. Okay? So there are some equations you can write down, which I won't try and describe in detail. But basically the point is that you need these O tilde operators to have a certain kind of, to have certain mixed correlators with the O operators. These mixed correlators in the eternal black hole geometry are telling you about the entanglement between the two sides. Now they're telling you that the two sides are entangled in a particular way, and that's what in the eternal black hole geometry fixes these mixed correlators. And you want to say that these mixed correlators in a pure state, for whatever these operators are in the CFT, and I'm going to try and describe how to construct these operators, have the same value as they do in the eternal black hole case, and this value is fixed by the entanglement that I mentioned. Okay, let me just point out one feature. Now these are some simple looking equations, but in particular one thing that you need is that these O tilde operators have to commute with the O operators. Okay? And that's simply the requirement that, if you think of one CFT, obviously all local operators in one CFT commute with all local operators in the other CFT. Okay, so they're just two distinct Hilbert spaces, and all operators on one side commute with all operators on the other side. So these new degrees of freedom, once you identify them in one CFT, have to commute with your ordinary degrees of freedom. So that's one requirement that you have. There are some other factors, these e to the minus beta factors, which come from the entanglement, which I won't elaborate on, but I'm happy to describe in questions if there are some questions later. Okay. Okay, so this is just a cartoon. It's the same thing that I said. To construct this field, you have left and right movers here. You extend the left movers into this, and you need some additional right movers. So remember, there are two descriptions of the field. One of them is valid outside, the other is valid inside. These descriptions look like they're discontinuous in some sense, but in fact, they're precisely what are required to make the field continuous across this point. The reason these descriptions look discontinuous is because of the coordinate system you've chosen. We have chosen a coordinate system which is a Schwarzschild coordinate system here and a Schwarzschild coordinate system there. Okay. And let me make a stronger statement. In fact, I'm going to try and show you in the next 10 or 15 minutes that all questions about the information paradox, all of these questions, including the strong subadditivity question, are basically questions about finding operators with the right properties in a single CFT. Okay, so these operators are the central issue in the information paradox is one of finding the right operators. Okay. Let me now describe how we can construct these operators, and then I'll describe some of the objections naively to why such operators should have existed and how this construction evades them. Okay? So the way...
Can you show me the properties which those operators will set?
Oh, sure. Is there some specific question you have about them? I just wanted to say that they're precisely phrased properties. If you have some specific question, I can. Basically, you need them to commute and to have, to behave like analytically continued versions of this chi by beta by 2. So if you think of the tilde operator, all of the tildes float to the right and they become analytically continued. Okay, good. So now the way you define them is as follows. Start with some equilibrium state. So let's say you wanted to describe these operators about some equilibrium state. Okay, and you think of all possible excitations of the equilibrium state by means of some operators. Okay, by means of some ordinary operators. Then you define these mirror operators. Consider the operators that satisfy these linear equations. Okay, so that for every possible excitation you can write down on top of this equilibrium state, this mirror operator acts in this form. Okay, so it gives you something on the right hand side. So this is specifying for you, the action of the O tilde operator on a certain excitation of the state. Okay, and the key point is that if you think of a heavy black hole microstate, a heavy black hole microstate can never be annihilated by the action of a finite number of ordinary single trace operators. Okay? Therefore, the linear equations that you get from here are all, these are all linearly independent vectors. You can never annihilate some heavy black hole microstate by acting with any element of this algebra as long as you limit the number of insertions. Of course, if I allow you to act with n insertions, then you can, but I'm not interested in what happens if you perturb the geometry by n insertions. Okay, that's a big perturbation of the geometry. I'm not interested in that. Physically, what I'm interested in is you start with a black hole microstate and you perturb the geometry a little bit with order 1, maybe even order root n number of insertions, but not enough that you can make the black hole vanish completely. Okay, and because of this fact that a heavy microstate can't be annihilated by the action of any finite number of single trace operators, this is specifying the action of these mirror operators on some set of linearly independent vectors, and in fact you can always specify the action of any linear operator on any linearly independent set of vectors. You can specify it arbitrarily. Okay, so I've specified it in a particular way, and in fact this particular way ensures that you satisfy the equations that I mentioned. I want to say that this is sufficient, but it's not necessary for a smooth horizon. What I've done here is I've imposed something that's slightly stronger than what I needed, which I'll mention again. I'll come back to later at the end of the talk. But the point is there's a very simple linear equations way of specifying the action of these operators. In fact, if you call these different excitations, did I put the... Yeah. So if you denote all of these products of O's as A1 to AD, okay, so there are different possible products of O's that you can have, then this gives you, all reasonable low energy excitations of psi. And later in this talk, I'll just use this notation A1 to AD. And whenever you say A1, it means some such product, okay, with some selection of frequencies and modes. Okay. And there's a maximum number of such products you have, which is the dimension of the small algebra that you get by multiplying together different O's, and that's D. And the key point is it's much smaller than the dimension of the Hilbert space. Okay. And therefore, these equations are soluble in all generic states. Okay. And in fact, you can explicitly solve them. This is a solution to those equations. You can define some metric on this space, and you can write down an explicit solution to these equations. Okay. And in fact, So let me just say something about them. So what I've done is I started with some basis state psi, okay, and I specified the action of some excitations about this basis state, and I call this smaller Hilbert space that I get, which is a subset of the bigger Hilbert space, I call this space et psi. Okay, within this space et psi, I've specified the action of these mirror operators, which are now ordinary linear operators. And you can multiply them, you can take expectation values, and these expectation values are precisely of the kind that satisfy the requirements that I had. Okay, so you can put these operators together in a local field to get smooth correlators across the horizon. Okay, now let me immediately say something, which is that what if you make a big change in the state? What if you want to ask what is the action of this operator O tilde, not on some state that's in et psi, but on some other state, which may also be a black hole microstate, but which is very far away in the sense that you have to act with a large number of single trace operators, but some with positive and some with negative energy, then what happens to this O tilde? Is there some way in some sense to stitch together, the O tildes that act here and the O tildes that act there into some operator that acts well on the whole Hilbert space? Okay. And this is a key issue, and this is this issue that I mentioned at the beginning about the state dependence of our operators, and I'll return to this at the end of my talk. But as I've defined them right now, they're defined about a given black hole microstate and about excitations of the given black hole microstate. Okay. This map that I've defined is actually closely related to something that people use a lot in the mathematical quantum field theory literature, and it's called Tomita-Takesaki theory. And the way you do it is you think of a certain antilinear map. So you have some algebra of operators, A alpha as I said, and you think of the antilinear map that takes S into A alpha dagger. Okay? This is an antilinear map. And these mirrors that I defined, those linear equations I defined previously, can be compactly phrased in terms of this Tomita-Takesaki map in this way. Okay? In fact, this e to the minus beta h by 2 factor also makes a natural appearance in this Tomita-Takesaki thing. It's what's required to make this antilinear map anti-unitary in some sense. Okay? This e to the minus beta h by 2 factor. And the key point is that these mirror operators satisfy the conditions we demanded above within all low point correlation functions. Okay? So this construction shows that if you use these mirror operators, you put them together in a low field, then in fact they predict that AdS CFT predicts that there's a smooth horizon and that there's no firewall. Okay? And as I said, this is closely related to something in the mathematical quantum field theory literature. And in fact, this issue of state dependence that I mentioned is related to another discussion there, which is a discussion of what's called the Korn's co-cycle, which I understand very little, so I won't describe it, but I'm happy to discuss later. Okay, good. Now, how do you use these mirrors to get rid of this firewall? I've said so far that you can use these mirrors, you can construct local fields, you can compute correlators across the horizon. They say the horizon is smooth, but what about these other arguments, the strong subadditivity argument that I showed you in the beginning, and these other arguments that AMPS have made suggesting that there's a firewall? How do these operators get rid of them? So let me just try and recount these arguments. And one way to phrase this argument, if I had to phrase all of this compactly, what I'd say is that Mathur and AMPSS and others have been arguing that these various arguments of counting and strong subadditivity, the genericity of commutators, which I'll describe, suggest that these O tilde operators don't exist in a CFT. And these are, I think, very good arguments, and they teach us a lot, but I think they turn out to be slightly deceptive, and I think there are loopholes in these arguments. But I'll describe these loopholes, and I'll try and discuss how this construction of the O tildes that I described sidesteps all of these arguments. Okay? Let me start with the strong subadditivity paradox, which I mentioned at the beginning. Okay? So remember I said that for the paradox, just to remind you quickly, was that you think of these three subsystems, A, B, and C, and for an old black hole, SAB has to be smaller than SA because B is purifying A, but B and C are entangled, okay? And that leads to a contradiction with this SA plus SC is smaller than or equal to SAB plus SBC. Okay? What's the resolution? Well, the resolution actually is simple, and it's very explicit in our construction. It's that these three systems, A, B, and C, are not independent. Okay, and you can think of this in terms of the spider web diagram, that these C degrees of freedom are actually made up in some sense of the A degrees of freedom. And there's a mathematical way of saying this in our construction, which is that these tilde operators don't commute with the ordinary operators. Okay? And that tells you that the degrees of freedom that constitute the system inside the black hole are indeed not independent of the degrees of freedom outside the black hole. So this lack of commutation is explicitly telling you that these two subsystems are not independent. And the strong subadditivity of entropy theorem applies only to independent subsystems. Okay? Now this is in fact consistent with old notions of black hole complementarity, which is the degrees of freedom in the interior of a black hole have an overlap with degrees of freedom far away. And this is also what's called A equal to RB by some authors. So there are many people who proposed similar resolutions, okay? Which is that A equal to RB. However, there's a catch in this resolution. This is the first resolution that one might propose to strong subadditivity, but there's a catch here. It's all very well to say these degrees of freedom don't commute. However, the problem is, what is the size of the commutator? How big is the commutator? So in general, if you try and say, I have one Hilbert space A, and I'm going to scramble some portion of the Hilbert space C, to construct the O tilde degrees of freedom by means of some unitary action on the O degrees of freedom, okay? Then it turns out that, because the Hilbert space is very big, the typical matrix elements of this commutator will indeed be small. But if you try and measure the square of this commutator, if you try and measure this kind of a 4-point correlation function, this is large. Okay? And you can estimate this very easily. You can do experiments in Mathematica. You can persuade yourself that in fact the commutator, the square of the commutator is large. Okay? And that's a problem. That's a problem because that's a big loss of locality. That's saying that someone behind the black hole and someone in front of the black hole, okay, these two friends who are on different sides of the horizon can communicate with each other. Because when this person acts with some O tilde operators, this person acting with the O tilde operators affects the physics as seen by this person who is acting with the O operators. Okay? So they can use this big commutator to write letters to each other. Okay? And in fact, it's this generic order 1 commutator argument that was a very powerful argument against the use of complementarity in this A equal to RB form to resolve the strong subadditivity paradox. Okay? How does our construction get around that? Our construction gets around that in the following way. If you think of this commutator, as I said, this commutator is not 0. However, within any low point correlation function, it's 0. Okay? So it's non-zero, but it's non-zero in an undetectable way. Okay? And you can see this from the equations I wrote. You can easily check that this O tilde always floats to the right of these A's, and the equations are in fact cleverly designed so that this commutator is not measurable within any low point correlation function. So this is what we sometimes call, saying that O into O tilde is dot equal to 0, which means it's not 0, but it's not 0 in a way that's undetectable in a black hole microstate and in small excitations about this black hole microstate. Okay? So that's how you can get rid of the strong subadditivity paradox, but you can also get rid of the superluminal propagation paradox that occurs if you didn't have this construction. Okay? Yes?
Some non-perturbative effect is important. Is that what you say?
Well, you can call it a non-perturbative effect. It's true you see this. Yes. Yes, it's true. You would see this effect, this non-zero commutator, if you really wanted to observe it. You would see it in an n-point correlation function. So the statement is that, within n-point correlation functions, where you've inserted, n or n-squared point correlation functions, you start seeing this non-zero commutator. So the idea of space-time breaks down if you insert too many correlators. That is, in some sense, a non-perturbative effect. In fact, as I'll try and mention later, perturbation theory does break down for these n-point correlators. You can think of it as a non-perturbative effect. But the precise statement is this. So an n-point correlator, you can't see it.
So this breakdown is exponential of what?
Well, it's e to the minus n squared. So if you think of an n-point connected correlator, okay, that's a right.
Exponential
of the black hole entropy.
Minus 1 over g Newton.
It's exponential of minus 1 over g Newton. Well, I'm confused by the factor. Yes, I think it's e to minus 1. Right. I mean, 1 over g Newton doesn't mean anything. That's a dimension full factor. It's e to the minus s, where s is the entropy of the black hole.
Yeah.
So you have to yeah. Okay. Good. So
even at the perturbative level, we cannot see the effect.
Yes, that's how this construction is getting around this. It's saying that there's some non-zero overlap, but this overlap is hidden in a way that you can't see it within perturbation theory, within 1 over n perturbation theory. Right. I'm going to say a little more about that. You're anticipating many of the things I say. Yes.
Of AdS or something like that doesn't make sense because
within the discussion of Hawking radiation, indeed, you will not see this effect, which is fine, which is exactly what you want. Within effective field theory, the inside of the horizon is completely independent of the outside. So you want to preserve that while ensuring that in some more complete description, there's actually some overlap between these degrees of freedom. So that's precisely what you want. That these regions look independent, but there is some secret overlap that you can't see, which you can see in the CFT, but you can't see in the bulk in any sense.
That become you're assuming that there's some sort of correlation between the point in the far interior of the black hole and the far outside of the black hole.
Yes, but
some sort of correlation.
Yes, it's a very subtle correlation. It's e to the minus n squared separate.
The correlation operators, it's effectively vanishing.
It's effectively vanishing. That's precisely.
Where you can find this kind
inside an n-point correlator. If in an n-point correlator, if you measure a very, very high point correlator, n is the central charge of the CFT. So if you think of a very, very high point correlator, then you can see this correlation. In fact, you'll see it here. This commutator is non-zero, and you can ask how many operators do I have to insert to see this non-zero fact. Turns out you have to insert n operators to see it.
So for example, if you consider some zero operators corresponding to this or something.
correspond to a?
The dual
To the Wilson loop. The Wilson loop will, well, I don't think the Wilson loop will help. The Wilson loop is probably, just some exponentiated single trace operator. That's not enough, I think. You might need something more than that. You really need black holes, you really need operators that correspond to creating a black hole. These are not operators you usually consider. So in fact, I'm going to say a little bit more about the breakdown of perturbation theory. So I'll come to that. That's also a good question, but I'm going to say a little more about that. Okay, good. Let me give you one more argument, that people had, and the argument was as follows. If you think of the normalized creation operator behind the horizon, this creation operator behind the horizon satisfies the usual algebra of creation and annihilation operators. Okay. However, if you think of the usual algebra, which is that C into C dagger is 1, it tells you that C dagger has a left inverse. This just comes from simple algebra. Taking C dagger equal to 1, it tells you that C dagger has a left inverse. However, creating a particle behind the horizon in this Hartle-Hawking state is like pulling out a particle in front of the horizon. You can check that in the Hartle-Hawking state, creating a particle behind the horizon is the same effect as pulling out a particle from in front of the horizon. Therefore, creating a particle behind the horizon in this particular Schwarzschild mode reduces the energy as measured at infinity. Okay. However, the growth of the number of states with energy is monotonic in the CFT. Okay. So how can you have an operator which has a left inverse but yet reduces the number of states? You see, the logic is very simple. The logic is, and this is the AMPSS argument. Sorry, I should have said here somewhere. This is the AMPSS paper. It's called the counting argument. The argument is this operator that acts behind the horizon, the creation operator, maps a bigger Hilbert space to a smaller Hilbert space because it reduces the energy. Yet it has a left inverse. But no operator that maps a bigger Hilbert space to a smaller Hilbert space can have a left inverse. And therefore, this operator doesn't exist. Okay, this is the counting argument. What's the resolution to the counting argument? The resolution is that, if you think of the action of this operator, of C and C tilde, it's, this is correct only within low point correlation functions. Okay? It's not actually equal to 1. Nor is it true actually that H into C tilde is strictly negative. Okay? So, this operator acts correctly on some region of the full Hilbert space, and it maps it to some other region of a big smaller Hilbert space. But the statement we are making is that H of E minus omega is smaller than this big Hilbert space, but this is irrelevant to the issue of how the operator acts about a black hole and about excitations about the black hole. Okay? So you can see that the loophole in the argument is that you don't need the operator to behave like 1 C and C tilde to have a commutator that's 1 as an operator. You need it to have a commutator that appears to be 1 within low point correlation functions. Okay? And that is not inconsistent with any linear algebra kind of argument of this kind. So it's the same kind of resolution where you need C tilde is dot equal to 1. Just like I said at the beginning, you needed O tilde is dot equal to 0. So you needed C tilde is dot equal to 1, which means it appears like 1 within correlation functions. And that allows you to explicitly construct these operators and evade this counting argument. Okay. There's another argument. This was made by Marolf and Pulczynski in their last paper on this. And the argument suggests, which again I won't review in detail, but I'm happy to have their questions about it, says that, if you take some operator O tilde, okay, some generic operator O tilde, then, the relation, the condition that acting with O tilde is the same as acting with omega star is some relation, it imposes some particular relation in the Hilbert space, and therefore some generic arguments tell you that it won't hold for a generic state. Okay? And so they argued based on this that if you think of the trace of the number operator as it's measured, okay, this trace of this number operator will in fact be order 1 in the microcanonical ensemble based on these general arguments. Okay? But you can see we can explicitly compute this for our construction. Okay? And I'm writing down an equation, although I don't have time to explain it. But just to indicate that you can explicitly do this computation of this operator, we have some construction of the O tildes, and you can explicitly evaluate this within a trace or within also on some typical microstate, and you see that you'll get 0 for this. Okay? So these generic arguments where you make some general argument about the expectation value of this operator, and then you try and argue this expectation value is order 1, explicitly fails for our case. Okay? And so, our construction has this explicit property that the infalling observer measures no particles at the horizon. Okay. Let me say a few things about about some features of our construction. One of them is related to the questions you were asking, which is about the breakdown of locality. So in fact, this is a feature of our construction, which is, as I said at the beginning, that this O tilde and O has a non-zero commutator, which you can measure inside an n-point correlator, okay, where n is the central charge of the CFT. Although I should say we haven't been very precise about whether you want it to be the central charge or the square root of the central charge. So I'm going to use n here as something that scales with the central charge of the CFT. And this is a feature of our construction. Okay? Now the question is there some independent evidence for this feature? That you expect locality to break down if you measure an n-point correlation function inside the CFT. Okay? And it turns out there is some independent evidence for this. And the independent evidence goes as follows. The first question you have to ask is, why do you see locality in the CFT, or why do you see locality in the bulk at all? Okay? And the answer is as follows. Think of the bulk Feynman path integral, and a local spacetime is some saddle point of this path integral, and all the local physics that you do is some 1 over n expansion, is some asymptotic series expansion of a correlation function about some saddle point of this path integral. Okay? However, if you extend this asymptotic series expansion far enough, then it breaks down, and then you have to consider the full path integral. And the full path integral doesn't have any good local properties, because to talk about locality, you have to talk about a background spacetime. Okay? So talking about locality in quantum gravity is essentially the same as talking about a saddle point of the full path integral and talking about 1 over n perturbation theory. So if you have a correlation function for which 1 over n perturbation theory in the CFT breaks down, and it breaks down in a way that you can't recast it as 1 over n perturbation theory about a different saddle point, that indicates a breakdown of locality. Okay? This is a general statement about AdS CFT. You can see that this does happen, for an n-point correlation function, and you can see this just by doing Feynman diagram counting. Okay? So think of an n-point correlation function, or think of a q-point correlation function. Sorry, I'm using q-point correlation function where 1 over n is the coupling constant. Okay? So think of a q-point correlation function. You can check that if 1 over n is a coupling constant, a tree-level amplitude has, of course, some number of powers of the coupling constant, which just appear because you take a large point amplitude, you get some powers of the coupling constant, but the number of Feynman graphs also grows. Okay? And in fact, it grows in a way so that you get q factorial into 1 by n to the q minus 2. The q minus 3 is not so important here. So it's q factorial into 1 by n to the power q. Okay? And this is simply from the fact the number of Feynman diagrams grows. You can see this in other ways. For example, you can use these new techniques to compute scattering amplitudes, and you can try and ask how many terms appear in these BCFW recursion relations if you think of a q-point scattering amplitude. And in fact, the answer is this. Okay? It's a slightly more complicated answer, but the leading term is correct. It's q factorial into 1 by n to the q minus 2. You can try and ask this question in string theory. String theory will in fact even give you the minus 3 factorial correct. Okay, it's because you have to fix 3 points. Why do they? Right. So right. Good. That's a good question. So good. So you have to estimate the correlation functions between these. So if you don't estimate the correlators correctly, you would actually take the square root of this. Okay. So you have to estimate the number of. You have to estimate whether these terms are correlated or not. Okay, good. So it's true that the way I've written it down, it's q factorial. Some naive ways of in fact computing these amplitudes would give you q factorial squared. Let me give you one way of computing this. If you try and compute a graviton scattering amplitude, just in flat space, and you try and compute it using these KLT relations, for example, okay, you'll see that the number of terms that appear actually is q factorial squared. Okay, it's not q factorial, and so the typical size is therefore q factorial. However, if there are some other ways of computing these amplitudes, like these BCFW recursion relations, they actually give you correlated terms, so that's why they add up. So that's a very good question. But the answer is that it depends on how you compute it. If you compute it, even if you look at these Cachasso, He-Yuan methods of computing these correlation functions, they give you in fact n factorial squared terms in the answer. But those are completely uncorrelated terms, so the answer is still n factorial. Okay. Now you can ask, what happens at one loop? And at one loop, it turns out there are more one-loop diagrams and there are tree-level diagrams. And you can see that by taking a one-loop diagram and cutting it into two parts. Just think, and you see that, and then you sum up the number of diagrams that you get in this manner. Okay? And if you take a one-loop diagram and you cut it into two parts, I don't have time to go through this right now, but the point is that there are more one-loop diagrams, and in fact there are more one-loop diagrams precisely by the number of external legs that you have. And this is a very simple counting that I'll be happy to go through with you if you're interested. But it's a very simple counting, and in fact it shows that for q equal to n, the 1 over n perturbation theory breaks down. So there is some independent evidence that suggests that 1 over n perturbation theory breaks down for a very high point correlator, and therefore locality breaks down for a very high point correlator, and that's consistent with our construction. Okay, good. Now there's this issue of the state dependence of our construction. Now this counting argument, okay, and the way I evaded the counting argument by saying that our operators act correctly in some small part of the Hilbert space suggests that in fact these operators may have to be state dependent, which means that if you're looking at some very different black hole, then to describe the field at the same point, okay, the field at what you might call the same point is in fact requires you to use a different operator in the CFT. Okay? And this is this feature of our construction which is called state dependence. And if you have this construction, then in fact there's some ambiguity in our construction. Let me just quickly describe what our ambiguity is. For example, I said that our construction has the property that the infalling observer never measures particles, but that's clearly too strong, because there are some states where where you create some particles just before the infalling observer falls in, and in such a state the infalling observer should be able to measure particles. And this is something that was pointed out by Busso and Van Ramstrong. Okay? So it suggests that you have to modify our construction for operators for states that are not in equilibrium. Okay? So how do you detect whether a state is in equilibrium or not? Okay, so and let me also say what you have to do to fix it. So what you basically have to do is fix this e to the minus beta h by 2 factor. Okay, the reason the infalling observer was measuring no particles was because of this definition I gave, which was that the mirror acted in this way, and there was this factor, and it's this factor that in some sense was fixing the entanglement between the inside and the outside. Okay, so I have to find a way to detect when the inside and outside are not entangled precisely correctly, because we know there are some states where they are not entangled correctly, and change this factor accordingly. Okay. And you have to change it with some unitary, and if you change it, this will predict excitations. So basically, the way you do it is you look at the time dependence of correlation functions. So you take some correlation function, you evolve it backward and forward in time, and you look at the time dependence of correlation functions. And if this time dependence is very small, if the correlators are time translationally invariant, then you declare that the state is in equilibrium. If they are not time translationally invariant, then at least we restrict to some set of states which are related to such time translationally invariant states by the action of some unitary. Okay? So these correspond to black hole states which are excited by some unitary operator. And then you can detect this unitary operator by using this time invariance criteria, and you can insert it precisely as I said you have to insert it, okay, in front, and this changes the entanglement between the inside and the outside and ensures that the infalling observer does measure particles, as indeed he should in a state of this kind, which is an equilibrium state which is excited by a unitary. Okay? This is a simple kind of ambiguity. There are more serious kinds of ambiguities. This is something that Mark Van Ramstrong pointed out. He said, what if your excitation is not created in front of the horizon but behind the horizon? That's what this e to the I omega tilde does. It's a left moving excitation that's sitting behind the horizon. Okay? How do you detect such an excitation? For excitations outside the horizon, you can detect them by looking at correlation functions of ordinary operators on the boundary. But what about an excitation which is some conspiracy to create some shock wave that's just behind the horizon? How do you detect this? In this, in fact, you look at these correlators. These correlators are time translationally invariant, because e to the I O tilde commutes with these guys by construction. However, if you think of the Hamiltonian, that's not. And the reason it's not is because when you create some energy behind the horizon, even though it's almost undetectable, it is detectable by means of the Hamiltonian at infinity. Okay? So the Hamiltonian can help you detect operators of this kind. And in fact, if you compute this correlator is 0 in an equilibrium state, and for this kind of an excited state which has a shock wave moving behind the horizon, it has some particular non-zero value, and by measuring the Hamiltonian, you can in fact detect such excitations as well. However, there are even more, there are some other ambiguities, and this is what was pointed out by Daniel Harlow in his paper on this topic. So this was his central observation, which was that, if you look at a correlation function, you define some new operators which are not our mirror operators, but related to our mirror operators, which have the property not only do they commute with the ordinary operators, they also commute with the Hamiltonian. Okay? What these operators are doing are creating particles behind the black hole without any energy. So in some sense, they're pulling energy out of the infalling matter and moving it close to the horizon. So you can't use the Hamiltonian to detect them. And in fact, at this point, we don't know how to detect these states, and they do create an ambiguity for our construction, although I believe this is something that should be soluble. This is work in progress, but I don't yet have a sharp answer to give to this part, this ambiguity. Okay, good. Let me just spend the last couple of minutes talking about a way in which you might be able to get rid of this entire state dependence problem altogether. Okay. And I want to emphasize that this argument that our operators have to be defined, on some local patch of the Hilbert space, in some sense is not inherent in our construction, but it comes if you accept the validity of these, AMPSS counting arguments, which suggests that no globally well-defined operator can behave correctly. Okay? And so the question is whether you can find some loophole and stitch up these operators that are defined on small patches of the Hilbert space in some way to give you a globally well-defined operator. So I'm going to describe very quickly some work in progress, although I don't have a full story to give you yet. Basically, the point is that rather than imposing the action of these mirrors on some vectors, you demand simply that they behave correctly within correlation functions. Okay? So within all energy eigenstates and all excitations of energy eigenstates by some single trace operators. Okay? This is weaker than what I demanded initially. So now I demand that the behavior of this is correct within a correlation function of this kind. Okay, it has some behavior, and I also have to now demand that the products of these operators have the correct behavior within correlation functions. Okay, initially when I didn't have this part, okay, and I was just setting the action of this operator, on a vector, then I didn't need to worry about products. The products would just come out recursively. Okay. In this case, I have to explicitly set, because the product of two operators, the product of expectation values is obviously, the expectation value of a product of operators is obviously not the product of expectation values. And so I have to independently demand that products of these mirror operators behave in this way. So this now gives you a slightly different set of equations. Okay, it gives you polynomial equations rather than linear equations to solve for these matrix operators. However, these polynomial equations are also generically solvable, and the reason they're solvable is that the matrix, if you count the number of matrix elements inside these mirror operators, in a Hilbert space of size e to the n squared, there are e to the 2n square matrix elements. Okay? And if you count the number of polynomial equations you had, they're only dA, which is the number of elements in this algebra A, into the e to the n squared. Okay? So in general, you have another undetermined set, and it is possible to solve these polynomial equations. Okay? But these obviously equations that are much harder to solve than our previous linear equations that we had, and so I don't have a complete story to give you yet about the characteristics of these solutions. But let me just mention that if you now want to stitch together these operators to construct these globally well-defined operators, then this utilizes some, the way this gets around this counting argument in some sense, which was the strongest argument for state dependence, is by utilizing a more subtle loophole. And the loophole it utilizes is that it imposes both of these conditions to be true only within correlation functions, and neither of them to be true as operator equations. Okay? So I didn't emphasize this enough perhaps at the beginning, but in my initial construction, this condition was something that you could almost impose independently as an operator equation. The fact that these O tildes had some commutators with the Hamiltonian, but now you want both of these to be true only within correlation functions. And if you demand this, then indeed you can try and stitch together these different O tilde operators that are defined in different parts of the Hilbert space into something that's globally well defined. And but as I said, this gives you a slightly different class of equations which we need to explore further. Okay, good. So I'm running out of time. Let me just summarize what I said. So I started off just by giving you a summary of all of these arguments in favor of firewalls and structure of the horizon. And as I said, the key thing to keep in mind is that it's possible to make all of these arguments well defined. Okay, so sometimes people encounter these arguments about the information paradox and they look very ill-defined, but in fact they are well-defined, and the way to make them well-defined is to think about them as questions about local operators in AdS CFT. And the central question, as I pointed out there, is whether you can construct the interior of the black hole within AdS CFT, which reduces to a question of the existence of certain kinds of operators. And then I showed you an explicit construction of certain kinds of operators, which though has, there's a question about that construction, even though it evades all of these arguments, which is about whether you can make these operators globally well defined in the Hilbert space, or whether you have to define them patchwise on the Hilbert space. Okay, and I concluded with some description about how you may be able to make them globally well defined. But I think this is a very interesting question, because it may be that you do have to define them patchwise, and then that would be something very interesting about quantum gravity. So I think there's a lot of stuff to come here, and I hope we'll have more to say in some time.